stationary state DFT, right? There was no time dependence. So today we're going to start with time dependent DFT, right? So, and this will be useful whenever I have time dependent potential problems like excited state or photoabsorption cross section and things like those. So just like stationary state DFT, the motivation here is to work in terms of the density, which now is going to be time dependent. Right, so the Hamiltonian here is some h0 plus v RT, where h0 I'll take as t operator plus v operator. So I have a time dependent potential, and therefore the density becomes time dependent, right? And what we want to show, just like in stationary state DFT, that rho RT is determined uniquely by a potential RT. So no two potentials that differ by more than a constant can give me the same density. So no two potentials by more than a constant that means VRT and some other potential V prime RT will give different rho RT. Is that okay? So now the thing to understand here is that one is talking about time dependent rho RT, and therefore the time dependent wave function need not be confined to ground state. It would be a mixture of many states of some stationary state Hamiltonian. So this is our goal. All right. Just to give you a background, because this was also initiated by Indians. First, it was proved for the time dependent DFT. It was initially proved by meaning this kind of theorem for time periodic potentials by Runge-Gross. Okay, this is JCP 1988. And then it was followed by work by Bartolotti, also JCP 1988. Bartolotti. Okay, so this is a limited time dependence. I'm talking about periodic potentials, but it's not so limited because many potentials that you apply, for example, light, gives you time periodic potential. And many times you excite by light or shining X-rays or something, It's useful in that. Alright, so it's
time periodic.
It's periodic in time. That means V RT is equal to V R T plus T. Period. It's periodic in time. Okay? E raised to minus I will get. Now, this is very easy to prove, and this was this kind of initiated the whole thing. And the way you do it is use floating. Approach to quantum mechanics or time-dependent quantum mechanics. A Floquet approach is something which is for periodic potentials. Alright? And this is based on what is known as Hill's differential equation. Okay? His last paper with me was on this, and I really say last paper you do yourself. I'm not going to do anything, so he did it himself. Okay, so, alright, this is an analysis of Floquet approach. Okay, so what it says is, if I have a Hamiltonian, which is periodic in time, alright, then the time-dependent wave function has a particular form. So, Schrodinger equation is I'm using atomic units, so this is equal to h psi, or h it minus h I d by dt. Psi is equal to 0. What Floquet says is that if h is periodic in time, as h t equals h t is t, then you can write psi as equal to some phi RT e raised to minus I et, exactly like steady state problem, where, and this you will, if you notice carefully, this is exactly like Bloch's theorem, where the potential is periodic in time, periodic in space, and now we are doing periodic in time. Right? And it's related to Bloch's theorem. In solids, where Hamiltonian is periodic in space, and your wave function psi r is equal to some uk r e raised to I k dot r. Right? So instead of periodicity in space, now I have periodicity in time. So instead of k, I have this IET and some phi RT, and if you like, for completeness, I also write E. Phi ERT is periodic in time, and E is known as the quasi-energy, because time-dependent system, so it cannot be the energy, but it's a sort of average energy, and this is the expectation value with respect to phi of I d by dt minus h phi, and then I'll put a double bracket, we also do time average. physically this is related to AC. Storm shape. Okay, so if you put a atom or a molecule in a periodic AC field, right, there's a shift in energy levels and this is going to find out. Alright, so now it's quite easy. We have mathematically we extended the Hilbert space from psi r to also include wave functions which are periodic in time, and that then time average defines over the expectation value with respect to r, and time average gives you the overall expectation value, and this is like the stationary state. By the way, I should also make here quasi energies defined module. Let's cross omega equals 2 I can DTH cross. Okay, so just like the quasi momentum blocks theorem is defined within the Benoit zone, in exactly the same manner E is defined at 2x cross omega. Alright? So, now that we've done all this, the rest is quite easy. What you can say is that, suppose two different V1 RT RT give the same density. Then one can show that E1 plus E2, where now E1 and E2 refer to quasi energy. That's the E1. That is the quasi. Alright? So you do exactly the same manner as you did in Runge-Gross theorem, except that now what you do is you take the time average also. Alright? And then you can do the rest of the things. You define exchange correlation potential, you define exchange correlation functionals, and all that.
Sir, so you define quasi-energy as modulo of omega.
It will come out to be modulo because these things are periodic. You can always absorb that extra omega in this. Just like you do in solid state physics.
So you just said that this omega is equivalent to the q vector
when you have periodicity in space. So this is periodic in time.
So in normal DFT, we did not meet this condition of periodicity of potentials.
We did not. Why should we?
But when we are doing time
dependent, this is the first attempt to do TDDFT. Alright? And I can prove a Runge-Gross like theorem if I extend my wave function to include periodic time. Is that okay? And then the rest follows because there is this I minus IT, so you can now do the whole thing, the T and EH and everything you can calculate, and then you can write time dependent, show you time dependent phone channel equation. Okay, and this then this implies the rest of the DFT machinery can now be typical. And when I say this machinery, it means including KS, TDDFT formulas. Once you there's a unique thing, I can write everything in terms of this periodic density, and then rest follows. Is that okay? Quasi-energy now can be written as a function of the density. Fine? Any questions on this? Okay, so this was the first attempt, and even now we do a lot of calculations which are time dependent. Excited state are done in terms of time dependent, periodic time dependent potentials. But this I must confess I do, because this is the first attempt in that too from India, so it has to be celebrated. Now we come to a general theorem. This is the statement of Runge-Gross theorem. Okay, and it shows that if two potentials start from differ by more than a constant time-dependent potential, then necessarily the density is going to be different. And the only catch in this is that since this is time-dependent problem, I have to have an initial condition. And that initial condition, we say that all, oh, you said pink is not good, right? Just so have to use something else. All wave functions evolve from the same initial wave function psi some 0 at t equals t0, where t0 is the initial time. So this we are going to assume, all right? And the Schrödinger equation is h I d psi by dt is equal to h0 plus v rt. And what we are going to show is that I'll write the equation for density and show that if two potentials start differing, whether by themselves or their higher derivatives differ, the density is going to be different as you evolve in time. Okay? So, what we are going to use is continuity equation. It says that d rho dt is equal to minus del dot j, where j is the current density, and j, I'm going to use only single r. Okay, it means summation I del r is equal to 1 over 2i psi star del psi minus psi del psi star. This is the usual definition of current that we use in quantum mechanics, right? Okay. Now I want to show that if two potentials differ, then J is going to be different. And if J is different, then we'll prove that means K also is different. Is the motivation clear? Motivation is this. And this is the root we have to take. So let's calculate partial J, partial T, which is going to be equal to 1 over 2i d psi star dt grad of psi minus plus psi star grad of del psi over del t minus del psi over del t grad of psi star minus psi, grad of del psi star over del t. I'll go over it slowly because this proof should be done well, and if you read the paper you get a little thrown off track. Okay, this is dj dt. Now let's substitute. This is going to be 1 over 2i d psi star dt is 1 over minus I. So this is going to be 1 over minus I, right? H0 plus B, is understood B is time dependent, so I'm just writing B psi star, and then you multiply by grad psi. That's the first term. Okay? Plus,
so in grad psi you don't need to put the value of psi?
what psi?
Psi's value or
No, this is oh, well, I'm calculating all this at t equals t dot.
and you are putting the value of psi star, so you don't need to write the psi star.
So I wrote psi star.
Yeah, grad psi.
She wants to use the same expression inside grad.
What is that?
Inside grad shell.
What about
Use the same
No.
expression.
But my question is that you are writing the value of del psi star by del t.
yes? And then I wrote del psi also. This I wrote, which is this, and this is here.
Yeah, but psi star, you are also writing the psi star, no?
Psi star is operating on psi star. H naught plus B is operating on psi star. What is the problem?
Maybe I am getting confused. I am just taking the value from this equation, cell I del from time dependent.
This one.
Yeah.
So this is minus I d psi star by dt equals H naught plus B r. Oh, there's a psi also there.
Yeah.
Okay? Okay, so for psi star, is psi star, right? Oh, this term I have written, plus psi star and grad of, right, H naught plus V psi over R. Is that okay? Minus 1 over I psi, minus 1 over I H0 plus V psi multiplied by grad psi star, right? Minus minus plus 1 over I psi grad of H0 plus V acting on psi star. Are you with me on this? Okay. Now this I can take out. It's easy, so let's put a minus sign here, and this will become minus a half. I can take out. I can take out. Just put a minus sign, and then plus I can take out. That's it. Right? Okay. Now suppose there's a different potential V prime, right? Suppose for a different potential V prime, I'll have dj dt prime at t equals t0 equals minus 1 over 2. All this will be replaced by V prime. Agreed? Okay? Now subtract, notice I'm doing at t equal to t0. So everything is at E0, so psi is the same. I'm starting at psi 0. Yes.
Shouldn't the third term be positive?
Shouldn't third term be positive? Yes, thank you. All right?
And the fourth term will be, yeah.
Okay? All right. So you get dj dt minus dj prime dt is equal to, you subtract, and you can see it very easily, you can come out quickly. Rho at t at t equals 0, grad of v minus v naught. You see this is a
So
minus
third
sign.
term will be negative, not
Huh?
positive. Third term will be negative, not positive.
This is negative. Second would be positive.
Yeah, and third one will also negative.
Third one would be negative because yeah, it's d psi by dt. Two positive and negative. Let me see if we get that correctly. dj dt comes out to be yes. This is the minus sign. Here. Let's keep checking this. Alright? I've gotten this, and I also have d2 rho by dt squared is equal to minus grad of j minus j prime minus rho prime will be equal to no, sorry. Will be equal to divergence of rho grad v minus v prime. Something is wrong. Let me see. dj by dt is okay. Now d2 rho by dt, that's it. There is a term here. Yeah, this is fine. Very good. Okay? Now notice, if so I've eaten a few steps from here to here in subtracting, and 3 or 4, no, 2 steps, and that you have to work out. If v and v prime differ at t equals 0, t equals t0, right? Yes.
So I don't think there will be two delta t.
What is that?
The last line,
Huh?
would there be two delta t? Divergence of j minus j prime.
J, no, this is dj dt.
So how you get this equation, del j by del t minus del j prime?
Because this is following from, I have d rho dt equals minus divergence of j.
Yeah, this I have understood, but second last one.
This one.
That how it is.
Or because I subtracted from this the j prime one. I wrote this, so let me write this. Okay, now that you have asked. This is my equation number 2 with prime. This is my equation number 1. So 1 minus 2. Yes. prime differ at t equals t naught, then RHS of delta dj dt is not 0. Alright? So that means the derivative of j with respect to t here and derivative of j with respect to t here is different. Right? If that is the case, then j's will differ immediately after. Right? This means right after t equals t naught, j will start differing. Right? If j's differ, I would expect that these also differ. Except that I have to prove that this can never be 0. Then d2 rho by dt square delta, that means d2 rho over dt square minus d2 rho prime over dt square, which is equal to minus divergence of rho gradient of v minus v prime, right? Will also refer if right hand side is never 0. And that means rho will, this is at t equals b, start differing right after t equals b, because the derivatives are different. Is that okay? Okay, now we have to show that this is not 0.
So basically we have shown that if the potentials are different, V and V prime,
And they evolve,
then the current evolves differently.
and so does the density. And if they evolve differently, they will start differing in time. As time processes, they will start differing. So the idea is very different from the Holmberg-Kohn stationary state, where we showed that if two potentials differ by more than a constant, we always have the same density. We always have the different density. Here we are saying that I'm starting with the same initial condition size 0, right? That means initial densities are the same, initial everything, but they start differing. The derivatives start differing as time evolves. Therefore, there has to be unique. So we are assuming two things now. Let me just write it here. We are taking all systems to evolve from the same initial wave function size 0, and number 2, taking VRT to be Taylor expandable. That part will come in a minute. About TC. The second part I have not used yet. Right now I have just used that the potentials may differ. Fine, that part I will use in a minute. Now, I still have to show that this right hand side is 0. Let us take kind of things which you do when you do electrostatics, particularly Jackson. Take divergence of V minus V prime, alright, rho, divergence of V minus V prime. This is equal to rho divergence of V minus V prime mod square plus V minus V prime divergence of rho grad of V minus V prime. Is that okay? So I've gotten a term here. Which is what I'm after, right? And integrate this. Integrate. Alright? Then for any finite system, by divergence theorem, this will be 0. Because this will be a surface integral. This will be integral ds dot V minus V prime rho grad of V minus V prime and it's 0 for where the density gets exponentially faster at infinity. This is standard divergence theorem. And on the right hand side, this is definitely greater than 0 because grad V minus V prime is non-zero, they are differing by more than a constant. So therefore this is definitely non-zero. Density is non-zero, so this volume integral is non-zero. And it will definitely be greater than 0. And left hand side is 0. Plus this, therefore, cannot. Zero. V minus V prime differs by more than a constant. If this cannot be 0, this better not be 0. So this is non-zero. Divergence of rho grad of V minus V prime is 1. You can go the other way. Assume that this is 0, then you show a contradiction.
So the same argument follows.
You can also start by assuming divergence of rho grad V minus V prime is equal to 0 and show a contradiction. Right? But then you say this is 0, this is positive, this is 0. So what one has shown is that the moment if the two potentials are different, right from the beginning, right, then the evolution is going to be different. The proof is not yet complete. One goes a step ahead and shows, suppose, now I'm going to use the Taylor expandable part. V I'm going to write as V equals 0 plus dV dt at t equals 0, t minus t0 plus r. Right? Now suppose the first part is equal. Suppose in the two potentials, suppose I have V prime, which still has this T0, T equals 0, plus this is different. Suppose this is equal, first part is equal. Okay? If the first part is equal, dj dt are going to be the same. then you will see that, okay, if I expand, if I write dj dt, which was what? Rho grad of v minus v prime at t equals 0. Then if I take, you can show d2j by dt square is going to be rho, because at t equals t0 this cancels. So I'll have to calculate the second derivative, which you can show. D rho dt part will come out to be different grad of dv dt minus dv prime dt at t equals 0. Then the second derivative will start differing. And the third derivative of density will differ. If this is the same, then the third derivative will start differing, and so on. You can keep building up. Wait here for a few minutes and see if there are any questions.
One thing, V and V prime are different both in space and time, right?
V and V prime are two different potentials which differ by more than a constant at any time.
At any time.
Right? Now we are going a step further and saying that V at t equals 0 could be the same, but their first derivatives differ. See, I am calculating everything at t equals t0. Right? All these differences are calculated t equals t0. So what we are showing is if the derivative are different, for j for example, the first derivative is different, then immediately after t naught we will start differing. However, at t equals t0, it may so happen that they are expandable that these two terms are the same. Then I will show dj dt will remain the same, but d2j by dt square will change. So again the evolution will be different. So you can do it term by term. That's why this Taylor expandability requirement is there. Okay? Any other question? So you can go all the way up to, so this is all this is taking form. Runge-Gross. Maybe I gave the reference wrong. I know it was not 1988. The Runge-Gross was 1982, I think, and this is 1984. Just follow it. Yeah. Let me correct myself. Runge-Gross and Adiabatic was, I think, basically 1982. Alright, so the other ones were Runge-Gross was for periodic, Adiabatic was for adiabatic is used on potentials, and now I've shown that Runge-Gross is for general. Except that the potential is Taylor expandable at the initial time, and I'm starting with the same function for everything. Okay, so in a way, what one has been shown is that the wave function evolves in such a way that a V RT is uniquely determined by each VRT gives a unique rho RT. Therefore, if I know it the entire time, there is a unique relationship. And therefore, V RT is a functional of rho RT, but what is not written explicitly but it is understood, it is also a functional of size 0. If you take a different size 0 to start with, the mapping may be different. We are assuming everything is size 0. I start with a different size 0, then the mapping will be different. And once you do this, then you can say that the many-body wave function, so IRT, is also a function of rho RT and size 0. Size 0 usually is not it, but you must understand this. Any questions so far? Okay, now we still have to look at the rest of the machinery. And the rest of the machinery is how to get the equation for the density. I'll leave for you doing higher orders. On quantum mechanics, for time-dependent system, there is this principle called Franklin. Radiation principle. It says that delta psi I d by dt minus h psi is equal. Notice that in this case, delta psi is only in the psi. Okay? It is not like delta psi, delta of something is a variation. However, now what we are going to say in TDDFT, this is how it is proved. Later, some papers came where this was emphasized. The delta of psi I d by dt minus h psi is, and this integration is defined from t0 to t. T0 is the initial time and some t1 is the upper limit. That's the variation principle. This is the action. And this is going to be a function of rho RT. It's understood. There's a size floating around which are not all right again. And this gives you the equation of the density. This is the equation for the density. To do this variation, you have to the equation of the density. Because all this action is a function of rho. So all the variation is going to be in terms of rho c, rho 1. How can I do it? Huh? 15. Okay. All right? Okay. Now that we've done this, delta A is equal to 0. And you put some condition on delta psi, whether it should be vanishing at T0, it should be vanishing at T1, and so on, that you can do. Okay? But this is the action principle. Now, Kohn-Sham system. So right now we have the action A developed. Approximations. Now the added complication is that in this the functional may be depending non-locally on space as it is non-locally on time. There's a time interval also, time integral also. Okay? So slightly more complications, slightly more subtleties that I'll leave. Just introducing you to the whole idea. Now, generally, just like the LDA, one makes adiabatic LDA, or known as ALDA, where the exchange coordination action or exchange coordination energy counterpart is defined as rho RT at that time, 4/3. Right at that time, there is no non-refracting time, that's why it's adiabatic. Right there. Otherwise, just like I have a gradient of rho r, there should be a gradient with respect to t also, which basically takes care of the non-locality in time. Right? So these are the extra circuities, and therefore this is slightly more complicated than stationary state DFT.
Sir, I don't understand what you mean by non-locality in time, because how can we take integral over past and future?
No, certainly from the past you can say that is the memory of the system. So if I change the potential out here, right, somewhere, if I change the density out here, it may affect the future potential.
Isn't that violation of causality?
No, if I change the density out here, it will change the potential later.
So what would be the limit of that integral in non-locality of time?
The non-locality of time may be very small, but you cannot rule it out. You cannot rule it out. It is a function of rho. Some change in rho will cause something somewhere. It need not be right there. It will have effect later. Thus, precisely that dj dt, d rho dt, all those terms are. Depends on all the derivatives. And derivatives means non-locality. Right? So that's what it is. So that makes it slightly more complicated. This is wide open, by the way. All this functional development, you come up with something and it will be very nice. Alright? Any other question? Okay. Now, what we are going to do is use all this formalism and this. We're just going to use it for excited state, although its application is as wide as any time dependent problem. Right? So, one can use TDDFT. Study. As I said, basic star shift. The good thing is that it gives you a way to handle the many electron problem, the electron interaction. Dynamic. Response, in particular, frequency. Dependent. Polarizability. Right? Scattering problem. Chemistry. Reactions and so on. I mean, wherever there is a time-dependent problem, you can apply it. Right? And what we want to focus on tomorrow is the excited state properties, which are related to calculation of time-dependent polarizability. This can be used to get excited state of an electronic system. Okay, also alpha omega. So let me just define polarizability. Is the dipole moment induced? In general, it's a tensor quantity, but let me just write it just like that. Alpha, you apply it. If I apply time-dependent electric field, particularly periodic time field, so I'll call it P omega, e raised to minus I omega t, is going to be alpha omega, some E0 e raised to minus I omega t. So if I apply a time varying, harmonic, pure frequency electric field, system develops a dipole, which is also periodic in time. So P0 omega equals alpha omega P0 omega, if you like. This is the dynamic polarizability. Okay? And this has a beautiful property that it blows up at omega equals the resonance frequency. Alpha omega tends to go to infinity at omega equals omega isolation. So if I calculate alpha omega as a function of omega, right, and see where it goes up, I found my excitation frequency. The machinery that is developed is that you extract it from the response function without actually tracing alpha omega over entire omega space. Okay, just to motivate you, let me just do the classical calculation and then I'll stop and then pick it up from there. So classically, if I have a harmonic oscillator and apply force on it, right? Then I can take the solution x t equals some amplitude x0 e raised to minus I omega t, and you see that you get x0 omega squared minus omega squared plus omega 0 squared equals f, or the amplitude becomes f over omega 0 squared minus omega squared. If there's a damping term, you get some I gamma omega also. Alright? And this goes to infinity at omega. X naught times q will be the dipole moment E naught omega.
It is somewhere similar like time dependent perturbation.
This is time dependent perturbation. Yes. And so alpha omega is proportional to 1 over omega 0 squared. Fine? And then you do the rest. Now, since you talked about perturbation theory, after I develop the entire TDDFT formalism, I can also apply it to in the perturbative form, that I have a system and apply only one perturbation and do the whole thing, because perturbation, I apply periodic perturbation and do perturbation theory. But this whole formalism that we developed, Runge-Gross theorem, that allows us to do that. Otherwise, we don't know whether I can even apply it to time dependent. So now there is a full just mathematical background that tells you, yes, you can apply and calculate all these quantities and do the rest of the stuff. Yeah, let's stop here.